This paper presents the development of a spatial, rigid/flexible dynamic model of biopsy and brachytherapy needles under the effect of a general force field. Percutaneous needle insertion constitutes one of the main practices for performing minimally invasive operations and covers a plethora of diagnostic and therapeutic applications such as neurosurgery, deep brain stimulation, and prostate biopsy. At the same time, accurate percutaneous needle placement is a highly challenging task due to various factors such as the limited visual feedback during the operation, the tissue anisotropy, and the variability in anatomical structures among different patients. To increase the accuracy of needle placement, different solutions have been proposed in the literature, such as the development of robot-assisted needle insertion systems and virtual simulators for medical training and preoperative planning. The first step towards the implementation of these robotic or simulation solutions is the formulation of mathematical models that can accurately capture the dynamics of needle insertion. In most cases, this modeling is divided into three main parts: the modeling of the soft tissue, the characterization of the interaction forces between the needle and the surrounding medium, and finally the modeling of the needle, which is also considered in this work. The development of the proposed spatial dynamic model of the needle is based on the floating frame of reference approach. The model consists of two connected bodies: the rigid base that can follow any arbitrary trajectory imposed by the surgeon's hand, and the flexible needle which is rigidly attached to the latter and deflects under the effect of a general three-dimensional force field that results from the body's interaction with the surrounding tissue. This interaction consists of distributed contact forces along the needle shaft and a point load at its tip. For the estimation of the flexible needle's displacement field, we considered two distinct implementations of the assumed modes method. These were the Rayleigh-Ritz and the finite element method. Both the reaction forces at the surgeon's hand and the vibrational behavior of the needle were obtained through the implementation of the generalized recursive Newton-Euler algorithm. To illustrate the performance of the proposed model, we considered a simple test case of step force loading. The system response was examined for both a fixed and a moving base. The results show that the proposed model captured the dynamics of the needle's vibration while accounting for the inertial forces and moments caused by the overall rigid body motion. Next steps will include the experimental validation of the proposed model.